Hey, so welcome back. We've been talking through concepts in preparation for the AP Physics C mechanics test coming up, and so we're practicing FRQs at this point. I've gotten this information straight from the College Board's website. It's public information. This was the 2019 test that we're going to be going through. I do want to point out, I think this is a great question to practice, actually. So it does a lot of technical things in this question, technical related to math and calculus that you need to know to be able to do. It's a great question, but it's a challenging one. So please pay close attention. If you can learn and understand how to do this question really well and understand the underlying concepts well, then that is a very good sign as you're preparing for your own exam. So let's go ahead and get started. I'll let you read through this on your own. I'm not going to read at you, but essentially you have an object that's dropped into a fluid and it accelerates as it goes down towards the bottom of the container, and then it hits the bottom of the container. And this is our data in the lower right. This is a picture of the system in the upper right. The first question is a free question, basically. Free points, more or less. It says, does the speed of the object increase, decrease, or remain the same? And of course, the speed increases throughout this process. So it doesn't get to a point where it reaches terminal velocity. By the way, let me mention that terminal velocity is a thing in fluids as well, meaning in liquids you can have a terminal velocity as well. You may have just seen this when you have an object moving in the air, but air is a fluid in a sense, and so are liquids. All right, so let's go ahead and continue with this. All right, number 2 for part A, it says, in a brief statement, describe the direction of the object's acceleration and how the magnitude of this acceleration changed as the object fell. So you may be overthinking this if you're thinking like positive, negative in that respect. So all they're asking for is the acceleration is down. It is accelerating in the downward direction, but the magnitude of the change of the acceleration, it's becoming less and less. It's decreasing as the time continues. I do believe that this strategy that I'm going to show you in just a moment is really worth 10 seconds of your time and thinking through. So when you're trying to go from a velocity graph to a acceleration graph, I'm going to remind you of this later, but really you take the slope of, say, 3 points along the way, and that will give you your instantaneous acceleration at those 3 points. You can plot those 3 points on a quick sketch for acceleration versus time and get an idea of what the acceleration is doing. Now you can do all of this in your head, but given the fact that you're probably going to be stressed and busy on the test itself, a question that is relatively easy like this question, you may get wrong just by being confused or not systematic. So I would suggest be systematic. So here's your strategy for how you're going to approach this. Again, just take tangent lines at 3 different points right here and just sketch those tangent lines and think to yourself, all right, the slope for these 3 points, you're going to have the greatest slope in the very first example here, a medium slope in the middle, and a slope that's nearly approaching 0, you could say, as it's getting to the top. Well, what does that mean? That means we start off with a relatively high amount of acceleration in a positive sense, then we have a medium amount, and then we get to a point where it's very low and it's actually approaching 0. It doesn't ever get to 0 with this data, but you could see how if this container was long enough, you could actually get to 0. In terms of the acceleration, that doesn't mean it stops, that just means it moves with terminal velocity. So to answer the question directly, you would say it accelerates downward, but the acceleration decreases with time, and the way you can justify that is just say the slope of the velocity graph gets more and more flat as time goes on. Something like that would get you the point. All right, and so A part 3 says, using the graph, calculate an approximate value for the magnitude of the acceleration of the object at t equals 0.2 seconds. So what that means is we're just going to take, like we said, a tangent line right here at t equals 0.2 seconds and calculate the slope. Now it's really crucial when you do this that you actually calculate the slope from 2 points on the line, not data points that they give you. They will not give you the points if you take 2 data points and do your slope calculation that way. And the reasoning for that is this. We are more confident about the slope of this line than we would be the slope from any 2 individual points. In other words, we're more confident about general trends and using data from general trends than we are from any 2 individual data points. So we never pick 2 individual data points for this calculation. So if you do the calculation, it turns out to be 2.22 meters a second squared. All right, and so now we're going to start getting into the drag force calculations. So it says the students use the equation given to model the speed of the falling object and find the best fit coefficients to be A and B, those given values. use the equation to 1. Derive an expression for the magnitude of the vertical displacement of the falling object as a function of time t. Let's think through how to do this. First of all, I want to emphasize they're giving us something, they're giving us a velocity function, and they're asking us for displacement. So I've created a graphic to talk you through this. You probably already know this, but I do want to talk you through these concepts here really quickly. So if you're given a velocity and you want to move to position, you're going to use integration if you want to go up effectively from this graphics perspective. And you're going to use derivation. You're going to use derivatives if you go down from top to bottom. And so just a couple things that students, little nuances that students sometimes forget or are not aware of that I want to stress. First of all, integrating gives you the change in values over a certain time frame, or a change with no set time frame if it's indefinite. So this is a good example of this. I'm saying if you take the integral of velocity, that's going to give you a difference or a change in position. A difference or a change in position would be displacement. And so that's why they ask about displacement here, even though I'm saying you have position, velocity, and acceleration here that you can work with. So when you integrate, remember you're talking about the change in those previous values. Secondly, an integral represents the area under the curve of a graph. So if we were able to take a integral of velocity with respect to time for a certain time frame, you take that integral and you end up with the change in position being equivalent to the area under that curve. You already know this, just reminding you of some things that you're aware of. Secondly, I do want to talk to you about derivatives really quickly. As a quick reminder, remember these are instantaneous values. So you can think of it really as a tangent line that touches a graph at only one point. That's an appropriate way to think about what we mean when we're talking about derivatives. If you decrease the time to be basically very little, then an extremely small amount, that's what we're talking about when we're talking about derivatives here. So we could say as a result, a derivative is the instantaneous slope of a graph. Just something to be reminded of. All right, so let's go back and think about what we're going to attempt to do. We're going to attempt to integrate this equation here, and that may also bring up some other issues for you. So let's think about how we're going to go about integrating this. All right, before we continue, I do want to point out this is part of your equation sheet. They do very kindly give you some very important concepts in calculus that you will need for this test and for the course itself. So if we're talking about the integral of e to a certain power with a constant out there, I've gone ahead and just taken a snip of this and expanded it out. We're going to take that and use that in our equation as a guide to help us to do the integral. So let's go back to that page where I had the problem showing. Alright, and so one of the first things we're going to do is set up our bounds at time equals 0 and time equals time. You could call this time prime if you wanted to, if this feels a little weird to write this for you. Time equals time prime like some, or time final if you wanted to. That's totally fine as well. Alright, so let's see how this works. And so keeping this in mind over here, what we can do is start the integral process. What we do is we draw out the a, because that's just a constant, bring it out in front. We've got our upper and lower bounds here that we're starting the integral process. The integral of 1 with respect to t is just t. The integral of this over here, you're going to end up pulling out this 1 over b constant over here. Notice we've got a negative value here. We also have a negative value here. We'll take care of the two negatives on our next step. And then this e to the negative bt remains more or less unchanged. So that's one of the special things about e. So we're going to continue with the integration, and all I'm going to do here is take care of these two negative signs and make them into a positive. And now I'm going to go ahead and plug in my t values for my upper bound and my lower bound. And so notice I do want to point out we've got e to the 0. That becomes 1. We do have a 1 over b expression over here. And we can simplify this if we, so to speak, we can sort of simplify this if we factor out 1 over b out of these terms over here. We're going to end up with this. And we can go ahead and plug in our values for a and for b that were given to us in the problem itself. And you end up with a couple more points on this problem. So that's how you would go about doing this. Let's see how the rest is done. So part 2 says derive an expression for the magnitude of the net force exerted on the object as it falls through the fluid as a function of time t. To get force, hopefully you can think through, well, what do we know? We've been given a velocity function. We came up with the position function or displacement function as a result of that. What else could we do? Well, we could come up with acceleration. And how does acceleration and force relate to each other? Hopefully you can come up with the idea that F equals ma. And so it makes sense that our next step would be to solve for the acceleration using this equation up here that they gave us for the velocity. So we want to solve for that function of the acceleration. So to do that, we're going to go about taking the derivative of the velocity function. So there are a couple things to note about this. This is going to be a little bit tricky as well, and so I want to talk you through some of the math with this as well. Notice you've got this times this, so we're going to use the product rule. And we're also going to have to use some of our knowledge about what's going on with this e value here too. So let's take a look over here and remind ourselves of the derivative rule with e. And so it turns out that if you take the derivative of e, that is to the power of ax, so some constant would be a, and then your function would be x over here, that turns out to be just bringing down that coefficient out in front, and then that e base times the ax power would remain the same. Alright, so back to our problem. So let's take a look at how we're going to go about doing this. The very first thing to mention is that we have to use the chain rule here. Unfortunately, the chain rule is not on your equation sheet. This is just something that you're expected to know how to do. So this I'll label as f, this I'll label as g. So if we want to take the derivative of these two expressions here, f and g, you would take the derivative of the first value times the second plus the first value times the derivative of the second. It turns out that if you take the derivative of a constant number, that's just going to be 0. So what that means is this part of the equation just drops out. So now we're just left with f times the derivative of g, which is the second equation that we have over here. So derivative of 1 is going to be 0, and the derivative of e to the negative bt is going to be negative b times e to the negative bt. So if we go ahead and continue, this is what we're ending up with. I need to clean up these two negative signs, and we end up with this equation. I'm going to label as 2, so when I drag it to the next page, you know what I'm talking about. But that will get you a point as well right there. And the next thing you're going to have to do is just use this idea of F equals ma, and we'll say, well, we need to multiply our mass here, and that will give us our force equation that we're being asked to provide. You can go ahead and plug in your numbers at this point as well for the values for the mass and for capital A, capital B, and you end up with this equation over here for the force as it goes through the fluid. Now that I should clarify, this is going to be the force that the object experiences as a drag force. There is another force. Think about what the other force is going to be. That's going to be gravity, right? So gravity's pulling it down. This is the drag force that's going to work in the opposite direction of motion, kind of like friction does. And so that'll all be going up. Okay, part C says the students repeat the experiment with the taller glass cylinder that is filled with the same fluid. The cylinder is tall enough so that the object reaches a constant speed. So if you remember, we had data that went kind of like this in an arcing path. Well, at this point, what we're saying is we extend the time long enough that it becomes flat at the ends. That doesn't mean it stops moving. That just means it moves at a terminal velocity. It does not get any faster. So it has a constant speed at the ends, and its acceleration is going to be 0 at the end. So let's reason through how to answer this. You can just write out the constant speed can be found by setting time equals infinity or some very large number. That's how to reason through this, because this is what we're starting from, and we're looking for the constant speed. Well, how would we know? Well, we would make this infinity and see what happens. So I go ahead and write out that equation. I'm going to throw in infinity for my time value right over here. It's true that if you have e to a negative infinity, what that means is 1 over e to an infinity. And that's going to be 1 over infinity, which is basically 0. So we can basically call this 0. And that's important to know how to do. If you need to review that and pause and think about that, that, by the way, will work for any number. You can throw in 3 to the negative infinity, 5 to the negative infinity. It's actually a good idea to practice this so you can get it in your mind ready to go when you need it. This concept that if you have e to the negative infinity power, that essentially leads to 0. If that is 0, that term is 0, then we're left simply with v terminal is equal to a times 1 minus 0. So that becomes 1 inside. And think about what we're saying. We're saying that v terminal is just equal to a then, therefore. That's how you would go about reasoning through this. Let's continue. So it says determine the force exerted by the fluid and the object at this time, justify your answer. So they're saying at this time. Well, what do they mean? They mean at the time when this thing is at a constant velocity. Justify your answer. So the way they give points for this, you could actually just justify this with words. But what I would do is actually justify this using a strategy I call the sum of the forces strategy. If you practice this enough, it becomes like second nature. It's like riding a bike. You don't even have to think about it, honestly. What I'm going to show you seems like a bit more work, but if you had to justify it mathematically, this is how you could go about doing it. So you go ahead and write Newton's second law. So Newton's second law is F equals ma, and in this case, your acceleration is going to be 0. And then you go ahead and you write the sum of the forces are also equal to, and you literally sum up the forces. We're going to call down positive here. That's just a preference thing. That's all. You can switch it up if you like, as long as you're consistent. Fg minus the maximum force that we're going to have for the drag force here. Then what we do with the sum of the forces strategy is we set these two things equal to each other and see what happens. So we end up with 0 is equal to these two things over here, and we prove that they are equal and opposite to each other. And you can go ahead and calculate some of this over here because you know what the mass is, you know what our g value is, and you end up with 0.12. Note, I do want to point this out too. Up until this point, depending on your teacher, most of the time you're going to be using 9.81, but I will mention on the test, on the AP test, 9.81 is close enough to 10 that you can get the right answer for any of these FRQs if you use 10 as your G value, and that will speed you up. And so I would highly recommend you just make this 10 and do your calculation that way. You'll still get the right answer. And so that was the end of this FRQ. This FRQ is very technical, but it's also very good. So if you can take a look at this and understand this, you're well on your way. I'm going to do more screencasts on the 2019, as well as other concepts related to this. I've got screencasts that go into the basis of what I just talked about. So if you had trouble with drag force, I've got other screencasts on this topic that you might want to take a look at as well. Let's continue to work through problems and get everyone ready for this test. Thank you for listening.